What else do we got? What kinds of math problems are there out there? Haven't done parallax.
We did gravity, we did angular
Parallax
resolution.
is the same thing as angular resolution, though. You're just
Um,
solving for lower d
haven't done
instead of
parallax.
theta. Okay. Parallax is the same thing as angular
To be
resolution, though. You're just solving for lower d instead of theta. Okay.
To be clear,
Before I drew an eyeball, now I'm going to put the object that we're measuring as a dot. We're measuring its distance, we don't care about its size. And then what we're going to do is we're going to pick a baseline over here that we'll call capital D. Okay.
You're too high.
Is that good? All right. So, this is how surveyors work. This is also how we do things in astronomy. So, I'm going to, and you're going to do a lab on this too, because I took the data for you 2 years ago. I took images of an asteroid called Haumea. It's a main belt asteroid. And at the same time, to within a second or two, a telescope in Chile observed it, and a telescope here in North Carolina observed it. So the Earth's motion was taken out of that. And the distance, the straight line distance between North Carolina and Chile, even accounting for the curvature of the Earth, is given in the lab. It's 0.55 of the Earth's radius. I won't do this example because that would rob you of the joy of doing this lab, but we'll keep it, well, anyway. What you see in the data, and what you're going to do is you're going to take these two images I took, and you're going to blink them. And what you're going to see is the background stars are going to shift, or the object's going to shift if you keep the background stars the same. And this isn't going to necessarily be your background, but there you go. So from Chile, you'll see the star appear to be between Saturn and this bright star. And from North Carolina, the asteroid will appear to be between this fainter star and, say, the moon. Okay, so the perspective shifts. So you can measure this angle here, theta. Okay, and you're going to do that using your measurement tool in Afterglow, which some of you guys. Oh, you haven't started that yet. We'll do that after the exam. Get you going on the first lab. The online students know what I'm talking about because they're starting to play with the first lab for Skynet. And then here's what we're after: the distance, d, to the object. Okay. The geometry is the same. The ratio of the angle theta to the full circle swept out by the red line is equal to the circumference of the full circle swept out by diameter d to that approximation of the arc that runs from across the baseline, like that. All right. So So theta is something we measure. D is a known. When surveyors do this, they use something called a surveyor's chain, which is a length of inflexible chain that is a standard length to measure, to do cartography basically. So we're going to rearrange this to solve for the thing we want, which is D. Do a bit of algebra, and we get that D is 360 over 2 pi big D over theta. Draw a box around that.
You want to scoot your board a little bit to the left.
Yay. This is giving you something to do. You're not falling asleep. Now, is that on your sheet, or are you going to need to remember how to do that? It is, but they write it out in words. So they say parallax, oops. They write parallax is equal to baseline divided by distance. Okay? But it's the same basic formula that we used for angular resolution. I'm just going to rearrange things a little bit.